Hi, my name is Alexander Huang, and my project is on noise versus clean data. What should diffusion model really learn? So, just a quick recap on diffusion model. It consists of two parts. One is the forward process, which you gradually add noise to the clean data, and the reverse process, we're trying to denoise the data from Gaussian distribution, try to recover the clean data. And you can train this process on two different laws. You can either predict the noise and trying to match the predicted noise with the true noise. This is called the epsilon prediction. Or you can try to train your laws based on um, clean data prediction, which is called X prediction. So basically, you're trying to match the predicted clean data with the true clean data. Um, and here's some experimental results on some examples that I run. So we embed 2D data into high dimensional space with a linear transformation. In this case, the dimension equal to 2, 8, 16, 32, all the way to 512. And we train two different diffusion models with epsilon prediction and X prediction respectively. And we try, and as we can see, at low dimension, epsilon prediction seem to be much better at reconstructing this example using the diffusion model. However, at high dimension, X prediction seems to outperform epsilon prediction. And you can see epsilon prediction basically outputs some basic some random Gaussian distributed dots. And the point of the project is to trying to explain why this happens. So we first test with the simplest example of any possible data set, which is a single point at high dimension. So we can see an so in X prediction, when we're predicting clean data, essentially when diffusion model is learning, we're sampling data points from various different noise level. And as long as we have one point at low noise level, we know this point must be very close to the clean data point. So we're able to have a very confident estimation of where the clean data is. So this explains why it's really easy to learn single point even at very high dimension space. As you can see, the loss curve immediately drops to zero even with we embed this point in 30,000 dimension space. And we do the same for epsilon prediction. And now the noise is distributed in a very high dimensional space, actually the same as the ambient space, which is 30,000 dimensional. And there's just too many degrees of freedom for the model to predict. And any small error in each component will accumulate to astronomical error in the complete prediction. So the model actually fails to learn anything. So the loss curve, as you can see, will stabilize it at 1. So at a high dimensional limit, the dimensionality is a bigger problem than intrinsic data complexity. That's why we see the behavior. And we do the same at low dimension. So when we are predicting clean data at low dimension, we test example on this dino data set, which is geometrically very complex. It's not convex or connected. And at high noise level, the clean data is very difficult to be predicted because from simply Gaussian noise. And what happened is the model basically tries to learn the mean and high noise level, and is able to learn the clean data still at low noise level. So what happened is in a reverse sampling process, this reverse sample point will travel to the mean first, but and when it gets to the uh, low noise regime, it's trying to go to converge to the clean data it's predicting. However, it doesn't quite have the time to make it. That's why we see a bunch of points between the jaws of the dinosaur and the fingers of the dinosaur. Those are the points that are halfway there. And we also do the same to predict the noise at low dimension. So this noise prediction task is essentially a residual learning task. And the predicting the change in this case, the noise is very regular because it's normally distributed, so it's very stable. And the dimensionality in this case is low, so it's tractable. So in this case, at the low dimension space, Data complexity is the bigger problem than the dimensionality. And the conclusion is uh, we essentially have a trade-off between tractability and regularity. Clean data is tractable but irregular, so it's better at high-dimensional space. However, noise is tractable but uh, regular, so it's better at low-dimensional space. So another question that we ask is, do we have a recipe to maybe balance the trade-off? Noise-dominated regime at high noise level, and maybe have a clean data-dominated regime at low noise level to compose the strengths of both behavior. Thanks so much.